So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to have Alexander Westphal come to us across from Germany. He's currently at the DSY, the German synchrotron, and he's no stranger to the Bay Area, though, as you'll see from his CV. He did his diploma at the University of Heidelberg on quantum mechanics and gravitation, and then went to Hamburg to do his PhD on higher dimension operators in high dimensional field theory. Then he was a research associate at the DSY and moved to Trieste for a short time. And then he came across and did his postdoc at Stanford University in the theoretical physics department. And then in 2010, he was a Helmholtz Fellow and remains a Helmholtz Fellow at DSY. And his career interests are inflation in string theory, extra dimensions and orbifold GUT theories, and also supersymmetry. And today he's going to talk to us about the landscape of string theory. So if you'll join me in welcoming Alexander.
Thank you. Thank you very much for giving me the opportunity to be at SETI. You know, I'm running on my computer and these screensavers that crunch the data. So I always kind of like look forward to ever be having a chance to come here. So I'm very happy to be here. And I will try to tell you something. This is a lot of, partially it's speculative stuff, I have to admit, because we don't know yet whether we can test anything. The first word we may be able to test in the next years. The other stuff, we will see. But there is some reasons to expect that, you know, from string theory, there is something very unusual coming in the sense that you have a second Copernican transition. You don't have one planet in the middle of the universe. You have many star systems and galaxies, but you may only not have only one universe. You may have many, gazillions of them. So basically, the background for the first part for inflation is basically that we have now satellites in the sky who have taken images from the cosmic microwave background radiation. I will tell you shortly what this is, if you haven't heard about it. And there is presently the most precise of them, the PLANCK satellite, has been taking its full 5 sky surveys. One of its instruments has run out of helium now as scheduled, so the data taking period there is over. But the analysis for this data will come out like a year from now, maybe, or something like that. We are waiting for this, very, very impatient. And then, of course, there's the big particle collider, right, at CERN, the Large Hadron Collider, which will hopefully at one point at least turn out the Higgs boson and maybe hints for supersymmetry or other new stuff. So it's an exciting time because we get new data in the next years about things that we don't know much about yet. So, but here I will talk about the evolution, things that have to do with the evolution of the very early universe. So this is a short time frame of the expansion of our universe as we understand it today. You see here in the present time there is one of these microwave recording satellites depicted. And then as we look out, you know that because of the finite speed of light, we look back in time. And for most of the time, like we can basically like gauge from different measurements, like for instance the distance of supernova, the older stars and the furthest away galaxies, and then from the cosmic microwave background, how old the universe is. It's like 13.7 billion years. For most of the largest part of this is of course filled by stars, galaxies, clusters of galaxies, superclusters. So there is some kind of hierarchical structure. But on the very largest scales, it becomes homogeneous. And then when you look even further, and because of the expansion, all the light is redshifted. Basically, its wavelengths get stretched by the expansion. Then you find that there is a faint signal coming from all directions in the microwave spectrum, actually, that is so much redshifted, a factor of 1,000, basically, that it was originally light of 3,000 Kelvin temperature, so like white hot. But it is now microwave light, and that came from the time when in the very early universe, which was hot and dense, when the plasma for the first time started to form hydrogen and the light could decouple from the free electrons and protons. this generated what is today the cosmic microwave background. And from this kind of light, we have now evidence of how the earliest phase of the expansion of the universe, if you want, just very, very shortly after the Big Bang, how that proceeded. And we have some evidence now that there is a process going on that is called inflation. And this process I will try to explain and what implications it has for our understanding of the larger universe. So I will basically make a big jump and ignore all the stuff that came after the very, very first microseconds and go back to the very early time. So what we have, or what we see when we measure this cosmic microwave background, that since Penzias and Wilson this is known, they were the first ones who saw this so-called 3 Kelvin radiation, 3 degrees over the absolute zero. For a long time, it was thought it was completely homogeneous. But then, since the satellite COBE, we know that there are tiny fluctuations in this radiation, very tiny, with a relative magnitude. When you just look for the variations in the temperature of the radiation, it's an almost perfect black body radiation. The variations in temperature are of order 10 to the minus 5, 1 part in 100,000. It's very homogeneous and isotropic, except for these tiny fluctuations, but they can be mapped. And when you basically look at the structure of these fluctuations, you can basically Fourier decompose them and then calculate a power spectrum of these fluctuations. You find that you can get evidence from how these fluctuations form, these tiny fluctuations. You can get evidence for instance, that most of the gravitating matter in the universe is actually invisible. It's dark matter. We only see it via its gravitational effects, among others, on how these fluctuations were formed. It's also the stuff that keeps, by the way, the galaxies together. If you didn't have this dark matter, they would just fly apart. They rotate too fast. And we also know of some kind of form, what some people call dark energy, that almost behaves, or basically behaves like the cosmological constant that Einstein already introduced and then later threw away by thinking it was complete nonsense what he was doing. But actually, this has been now measured, that there is a very, very small value for this quantity. And it has the funny effect that it kind of speeds up the expansion of the universe. It accelerates it, which no one had expected before they found this, like in the very late 90s. I mean, like the supernova, the 2 supernova things, they got the Nobel Prize for this discovery first, that the expansion speeds up. So, and then the final thing is that people notice that if you take these tiny fluctuations, they cause variations in temperature, but therefore also in density of matter, and therefore of variations in the gravitational potential at that time. And you put this on a computer, run it forward, you find that these tiny fluctuations generate all the large-scale structure of the galaxy clusters and superclusters we see today in our universe. So this is relatively well understood, basically, that you can really show that wherever you find like deviations from the mean temperature, you find clusters or voids today. You can really map that, like an atlas. So this is basically how this, the fluctuations distribute. And overall, you see that they basically they average out, but you have, of course, the local tiny, like 10 to the minus 5 magnitude fluctuations in temperature. And this is when you basically the kind of result that you get from that when you Fourier decompose it and compute the power spectrum of the 2-point function of these fluctuations. You see that there are distinct structures in there. There are waves, sound waves, basically, that propagated through the hot plasma before it cooled enough that hydrogen could form. So, and the point is that when you analyze these precise properties of these fluctuations here, you see that besides all the local dynamics, like sound waves, the way how the sound waves interact with the plasma, the way how the plasma interacts with the photons and the electromagnetic fields there, overall you find basically a very remarkable structure. You find that the sound waves were generated that caused these tiny fluctuations in the temperature. These sound waves were generated with basically having the same power on all wavelengths. So they have a so-called scale invariant power spectrum. And they come all with an initial coherent phase condition, as if they were coming from a broadband laser, if you want. And furthermore, you can show that some of these fluctuations, they are in phase, the initial phase, they are coherent, but they have a wavelength which is so big that at the time that they were forming, which is about 400,000 years after the Big Bang, they could never have made the distance between like different parts of the sky at that time. So they were out of causal contact, but still they maintained this coherence. And this is basically, it's very strong evidence. I would not say it maybe proof, but there's very strong evidence. I mean, proving you can't anything, anyways, but it's mounting and getting stronger evidence that there was a very early phase, much earlier than this 400,000 years of the CMB, during the first micro of, like 10 to the minus 30 seconds after the Big Bang, that there was a very early phase of the expansion of the universe, which was much faster than anything we have ever seen since, which was actually exponentially fast. And this is called inflation. So the original motivation for developing this, even before you knew all about these cosmic microwave background fluctuations, like back in the 70s and 80s, was this kind of phenomenon. This is a kind of sketch of our universe, how we can see it. We are sitting somewhere here where this guy is. We look backwards. And when we look backwards, we look back in time. And this is basically the last signal of electromagnetic light that we can see. This cosmic microwave background radiation that came from the then hot plasma, 3,000 Kelvin hot plasma. That originated about 370,000 years after the Big Bang. We have evidence from theorems by Hawking and Penrose that already this radiation is enough that everything had to fall back into itself in our past, and there was a singularity. There had to be a singularity of gravitation, an infinite point of gravitational strength where everything would crunch back into itself. So we know that this is basically, there is the beginning of the time inside our universe. And 370,000 years after that, this radiation was formed. This is the farthest we can see. After that, we have plasma. It is opaque. We can't look any further with electromagnetic radiation. But the point is, we see that this is, as I said, on equal temperature, on all this huge sphere we see in the sky. You can now basically estimate how big that huge area, like 20 billion light years of diameter, was at the time when this thing was formed. The universe was expanding since then, right? It was smaller, but it was way bigger than anything a light beam could have reached from the time, from the very beginning, in that time of 300,000 years. The sky was much bigger. So there were many areas that could never have talked to each other, at least by causal means, by means of stuff that is consistent with special relativity. So then you wonder, why do I have so many areas that could have not talked to each other, but they sit all at the same temperature to 1 part in 100,000? So there are two options. Either you assume a miracle, that somehow this is just completely sitting at the same value for some unknown, who knows what reason, or you look for a mechanism that somehow made this thing come in causal contact further in the past from one region where light could have been, where everything could have averaged out by causal mechanisms. And that's what inflation was invented for. So this is basically, So in order to basically tell you how inflation then works, I have to very sketch you how you describe the expansion of the universe. The expansion is described in terms of its the differential rate by which the size of the universe increases. So let's call R the distance to the largest scales we can see, which is roughly this 10 billion, 20 billion light year scale. Now the dot is the time derivative. That means just the change, how fast the thing gets bigger, and you divide it by how big it is. And this is the quantity that you call the Hubble constant or Hubble parameter. This is basically by how many kilometers per second things recede away from you as a function of distance. Right? This is the Hubble law that is behind that. That the further things are away, the faster they recede from you. So the thing is that when you go to how to describe the dynamics, which is of course Einstein's theory of general relativity, you find that this quantity is linked to the overall curvature of our four-dimensional space-time, that is our universe. And it is determined by how much matter and energy you have in the universe. This is basically, in words, how the equation reads for the dynamics of our universe. And in matter and energy is everything. It's radiation, it's the stuff that sits here, it is gas, it is dark matter, it is also dark energy, and it is also kinetic energy if things are fast moving. So you have to basically look at this and then see how this drives the expansion of the universe. And the main point is that there is one source of energy, which is if you have something like what is called a scalar field. Scalar field is a field that is not, the electromagnetic field is a vector field. It's like you have the magnetic field is a vector, the electric field is a vector. Then you have other basically fields that have anti-commuting properties that make up our matter, like the electrons. or the quarks. But there are also fields who have no direction. They have no kind of directional property. They are just a number at each point in space and time. Just a function, if you want. And these are called scalar fields. Now, these things, they can move around, like they have a wave equation, like the electromagnetic waves, but they can also have a potential energy. So something like if you want the position of a ball that I'm lifting up is such a scalar field, and this position, if you want, gets more energy if I lift it up against gravitational potential, right? So that is just an analogy. But in this way, a scalar field can have a potential energy. Basically, when it takes different values, it has a different amount of energy stored just in its own state, so to speak, without even moving. So the point is that if I get to a situation, if I can engineer a situation where this potential energy is the dominant part of the energy in the whole universe, everything else is subdominant, then I get that the universe expands exponentially fast, faster than anything that the radiation or normal matter can do with the universe. It basically doubles its diameter on a fixed rate, on a fixed time scale. Always doubles and doubles and doubles again. It goes so fast in the expansion that basically there's a distance scale, like in the typical models of this, it's expanding so fast that light that emanates from my hand could not make basically it to my eye, because the space in between would be expanding so fast that the light would basically be kept back from ever reaching me. This is what will happen if you have exponential expansion. So the idea would be, you have to cook something up where the scalar field initially just stays almost quiet, and only after some time starts to roll quickly and basically get rid of its potential energy. Because once it's down here, by energy conservation, it has converted into motion, kinetic energy. It will fluctuate around. Then it does not drive exponential expansion anymore. So I will very shortly, these are the only two equations you have to unfortunately see here. I will very shortly describe how this works, how you can engineer that. So this is the equation of motion, just the time, the evolution with time of such a scalar field that has a potential energy in an expanding universe. You see the Hubble parameter, the rate of expansion appearing here if you want. Now, the point is you can look at how you make the scalar field very slowly evolving so that its potential energy is dominant, and that would mean that you scrap this one here. Right? I mean, you scrap the acceleration part, and you have to have an equation that only balances these two. Then it will move very slowly, evolve very slowly in time, and then its potential energy is dominant, and you get the exponential expansion. So the easiest way to do that is, of course, that you make this thing almost zero. You make it the potential very flat, very shallow. Then you can reach such a kind of state. So this is exactly what you're going to do. You're trying to build a potential which is very flat out here, very shallow. Then the Hubble parameter is almost directly given by, as I said, by energy and matter, and the only energy form is then the potential energy. Then it's almost constant because the field is moving slowly. And then you plug that just in the definition, and you get exponential expansion. It's just the differential equation for an exponential function of time. So this is basically what you have to do. You have to find a scalar potential that basically gets the field rolling very slowly, right? So that only after some time it picks up speed. So the simplest potential that does that, goes back to Andre Linde in 1982, is just a parabola, a parabolic, whatever, ball, so to speak. So that means just you have a scalar field that has a mass, that is not massless. So the point is, normally you would think, the scalar field would settle in its minimum. Here's the minimum of the potential energy. But if you somehow manage to crank it up to some value here, and the value is high enough, then it will drive automatically, because of this form of the parabola. It will move so slowly that because the potential energy it has here basically damps its motion. It's like a viscous liquid in which it moves. That it will drive exponential expansion. And then you have your idea of inflation realized, and you get a humongously big universe in a very short time. And everything that you see today would then come from a very tiny region in space and time. So this is how the expansion, how it proceeds. Basically, once you have such a situation, the volume of space doubles extremely fast. It uses extremely fast. It becomes very, very, exponentially fast, becomes extremely big, and everything that we can see today could come from a speck of space and time that is, more tiny than my finger. In particular, it could have been in causal contact at the earlier times on. There is no problem then to explain why everything is so homogeneous. Yeah? This is basically what happens, for instance. Imagine that when this process starts, your universe is small and highly curved. It's like a ball. It's not flat and big. But if you get this super fast exponential expansion, what it does, it will make the ball exponentially large. And if all we can see is just some area here, then on that finite area, we will, after enough of this exponential expansion, we won't see anything of the curvature of the total ball. Everything will appear completely flat to us. So this is how we can basically manufacture a very our isotropic and homogeneous universe, even from something that may not have been homogeneous and isotropic at all at the beginning. So now, this was just the story of how to get this expansion to work, how to get this very early phase of exponential expansion that is called inflation. Now there is a crucial property that inflation has once you take quantum mechanics into account. Of course, we do not know yet what a quantum theory of gravity is, but what you can do is you can quantum mechanics of fields like a scalar field in an expanding space-time. That you can do. We have good rules for how that proceeds. And then you work out basically what happens. The scalar field that drives inflation is not just a classical property, it has quantum fluctuations. Like a particle, like an electron that you put in a box or something like that, and the box is tiny, then it has a 0-point fluctuation, a motion that will never completely cease because of the uncertainty principle. And this kind of 0-point motion will cause the field to fluctuate. And when it fluctuates not just in some, like Euclidean or Minkowski space, like around us, flat space, but in some space that is expanding very fast, exponentially fast. You call that de Sitter space. De Sitter was the first guy who actually wrote down the metric that describes an exponentially fast expanding space-time. If you have quantum fluctuations of your scalar field in a space-time that's expanding exponentially fast, then you find that whenever there is a fluctuation, it's rapidly stretched in wavelength because of the expansion. And at the moment, it becomes basically, it goes to the length scale. As I said, that light can only travel before it basically, the expansion, the pull points recede faster than you can ever communicate between. The fluctuations get classical, they get frozen. It's like you have, if you want, you have all these quantum fluctuations, and the extremely fast expansion, by stretching them, plucks out all the longest wavelengths and makes them into classical modes. And this explains why these fluctuations all come out with the same phase. In a sense, it's as if this superfast expansion acts like a laser for converting quantum fluctuations in basically classical fields. So now the point is, of course, these quantum fluctuations, once they become classical, they carry a little bit of energy density variation, right? Because the field goes up and down in its value a little bit. And these fluctuations in energy density cause fluctuations in the gravitational field. And these are the sources of the fluctuations in temperature in the CMB, which then source later on all the structure in the universe. The tiny temperature variations, that is at least the hypothesis, they come from these quantum fluctuations in this extremely early and super fast expanding phase of the universe. They cause basically later the temperature flucturations. So if this is true, then all of us, we are sitting here, we are basically a product of these tiny quantum fluctuations during the inflationary phase of the universe that are then stretched, made classical by the superfast expansion, and later cause the temperature fluctuations in the plasma. So that basically explains that story. Until basically, that's the part about inflation that you can measure, right? You can now write different models of these, like how to make this potential flat. Then you calculate how these quantum fluctuations exactly look like, and they will give you slightly different variations in the form of the temperature fluctuation, and you can compare. This is why they are building the satellites, to trying to map out these fluctuations. So basically, to give you a short picture, is basically this is what I told you before, right? Once you have these fluctuations seated in the temperature coming from inflation, then they will collapse under their own gravity over time, and they will form all the structure that we see that has formed since the CMB was released. So they first collapse, and basically they form hydrogen clouds, the hydrogen clouds which sit at the bit over dense regions coming from regions of if you want a higher temperature, a little bit higher temperature, they collapse into big gas clouds, then form stars, galaxies, clusters of galaxies. I mean, there is a hierarchical clustering that comes from the action of gravity on all these structures over time. And you can basically, as you see, you can map kind of like these overdensities, these clusters to the, so. Now there's one additional point that I want to make, is that beyond these fluctuations in density and temperature that we see in the cosmic microwave background, we see then later evolving into the structure around us in the universe, is that during basically all the fields that you have in your universe, they fluctuate. They have quantum fluctuations, not just the scalar field. It's also the gravitational field that fluctuates. And very weak form of these fluctuations you can calculate without having to know a full theory of quantum gravity. So that means basically that also the gravitational field fluctuates a little bit, and that produces gravitational waves. And they are plucked, the long wavelength zones are plucked out of their quantum mechanical origin and are made basically classical by the very fast inflationary expansion too. So the thing is that besides, so to speak, the density variations, inflation also causes real gravitational waves that are propagating, and they have been propagating ever since. And these things, what they cause in the CMB is they cause polarization patterns. The polarization, if these waves are there, is no longer completely like stochastic and random, but there are patterns coming from these gravitational waves, and if they are strong enough, you can see the polarization pattern. This is another thing that satellites like PLANCK are searching for, and several ground-based experiments actually, like the South Pole Telescope and some other observatories, they look for this polarization pattern. The point is, if you could see it, you would basically directly see the energy scale at which the exponential expansion of inflation took place. If you see it, we can basically work it out, which I can't do here now, but you can show that if the existing experiments which are running, if they see this, then inflation happened at a scale of energies which was only maybe 100 times smaller than the scale where gravity becomes a strong quantum effect, the so-called Planck scale, where the strength of the gravitational interaction is the same as all the other interactions, and you need something like string theory, for instance, to really describe that. Yeah? So the hope is that if you could see this gravitational wave signal coming from inflation as basically the complementary fluctuations of the gravitational field that so to complement the density fluctuation, which we have already seen, then you could directly measure the scale, the energy scale where inflation happened, and maybe you can learn something about, because it is so close to the Planck scale, about what happens when gravity itself has to be quantized and become a full quantum theory of gravity. So the thing is that for my later discussion is that you have to take away here is that when you want to make models for this, for something that produces enough gravity waves to be seen in the cosmic microwave background sky, you have to basically make models where the field, the scalar field itself, rolls a long distance while it does the exponential expansion. Long means, since these things are all basically written in terms of, if you want the gravitational constant, which gives you the Planck, the energy scale of the Planck mass, where gravity becomes strong, you have to move more. The field, the potential has to be such that you move a large distance in field space, more than a Planck unit. And you find that the only things that do that, the only kind of shapes of scalar potential that you can write down that do that, are ones like the simple bowl, like a quadratic shape, a parabola. You can make a different power here, phi to the fourth, let's say, or phi cubed. Phi cubed doesn't have a minimum, but anything that has a minimum. But it must be some kind of power law. These are the only ones that really do that. And then the question will therefore be later, because these ones sit so close to the fundamental scale of quantum gravity, can you make them in string theory? Can you learn something about how string theory does such models? Maybe there is then structure that you can basically try to test. So but before we come to that, I would basically now tell you what these fluctuations really, what they really cause when you look further into them. The point is that you can ask what happens if I have a region in my scalar potential which is not just shallow, but completely flat, basically. At that moment, the fluctuations of the scalar field can drive the field back up the hill. Because if the hill is extremely shallow, the speed by which the average size of these quantum fluctuations have the field jumping around can be bigger than the speed by which it still wants to roll down the hill. And then you can go uphill. which classically you never could do. Quantum fluctuations can get the field jumping uphill. And when it jumps up the hill, where the potential is very flat, you get even more inflation. And when you get more inflation, you can just have time to wait, and it will jump again. And you get even more inflation. Once you have such a regime, inflation does never stop. It stops in some regions of space-time, but not ever. But globally, it will never stop. There will always be some region where the field jumps uphill, and you get more inflation. And that means inflation becomes eternal. So this was also by Andre Linde. He was I think the first one who really realized that you get this eternal process of reproduction. Yeah? So this is what happens. If your initial region of space-time was inflating, then it gets bigger. And in some regions of space-time, the field rolls us down and inflation ends. In some other regions, because of the quantum jumps, it may have jumped up the potential. And then inflation goes on there and goes for longer. And basically, those regions where it jumped up, they still expand exponentially and basically cause they are themselves regions which go further on with the exponential expansion. Of those ones, still parts may roll down and end. But some parts will again jump up. And this goes on and on. You get basically like a big fractal, where some part of the fractal is forever going through exponential expansion. Right? This is what you call the process of eternal inflation. And if that kind of picture is true, then of course you know that there is a region of space-time which is infinitely big, which we will never see and have never seen. Then our universe is an extremely tiny speck of the amount of space-time that is there. Our whole universe is basically like a spot of, I don't know, less than a spot of sand compared to our universe. I mean, the ratio between the spot of sand and our universe is bigger than the volume of our universe compared to what you get out of this here. Yeah? And this is basically like, I will show you here, this is a simulation for this bowl-shaped potential. What happens if I let the field start at some value, I let it roll down the quadratic bowl, but I will also add the quantum fluctuations, these jumps that typically they get from the quantum uncertainty. And when you see what it does, it gets the field first fluctuating. Some regions roll down, downwards basically means the field gets smaller and you get smaller energy, but some are grow and grow and grow, they never stop. These regions up here, they are so high up in this bowl-shaped potential that they drive unimaginably fast exponential expansion. And they go further up because the quantum fluctuations get stronger, the more potential energy is there. So you will never stop. I mean, all these tiny islands in between where it went down, and basically you have seen that here are coordinates of space, right? But I rescaled them by the exponentially growing size, scale size of the universe, R, right? Because otherwise this whole box would continuously exponentially grow and I couldn't draw it. But that means every tiny island where the field has rolled down and inflation has ended is something that is already probably as big as billions of light years. But the other regions are much bigger. And they never stop to grow. So this is in a way how you can try to simulate something where you generate many, 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 many local universes surrounded by eternally inflating space-time from some kind of computer simulation of the dynamics of this system. And this is why people say that if you take inflation seriously, there have to be many more space-time regions outside our own one, which are still huge, and there are probably infinitely many of them. There is what they call a multiverse. Yeah? So this is basically what I just said. I mean, that you get many of these, you get infinitely many. And this is just with one bowl-shaped potential. You already get infinitely many causally disconnected regions that cannot talk to each other, which may each of them be as big as our own or even bigger, and embedded in an even bigger, infinitely big region of eternally inflating space-time. So once you have this multiverse, I mean, there is now a twist to basically here. This is the simplest version. But the point is, of course, what happens if the potential has more than one minimum? It could be something like a mountainous landscape here, right? Imagine this is now basically, I mean, look, this is the potential energy of, let's say, two scalar fields, right? Before I would have said this is just a bowl with a quadratic shape. Now I say there could be many bowls with quadratic, that look quadratic around the origin, but they could be like it could be like like a mountainscape if you want. Okay, if you have that, then you have that in every local region where basically the field can get trapped, where it can like a ball roll in. and which has positive potential energy, it does inflation. So, and it does generate an infinitely large number of domains, of regions, where the field is moving somewhere around here. So you get now, even on top of that, that you get infinitely many universes, you get even that, a different subset of each of these infinitely many universes may have the field sitting in different regions of its scalar potential. And that is what, if that situation is realized, is what you would call that you have a landscape of different local minima, local regions where the field wants to roll, each of them infinitely often realized by eternal inflation. You have a multiverse where basically you don't only have different regions of space-time, infinitely many of them, but there may be different values of scalar fields in them, hugely different. They may even change the constants of nature.
Question?
Yeah.
So in this multiverse concept, which I'm trying to understand here, if we're in, one section or another, and everybody did their own W map, they would have a different W map plot?
Yes, they would. I mean, the point is that you can, if you allow any kind of observer that not necessarily has any remote, that does not look like us, doesn't use our kind of, carbon physics or carbon chemistry in order to form. If it could be just like, the observer may be some combination of photons that may have intelligence, whatever, something like that. Then they could live in a hugely different universe, and they would see a completely different CMB. Could be a very hot universe that is not basically where the fluctuations are much bigger. And
so that means that no theoretical physicist in any one of these multiverses could talk to the experimentalists and get an estimate of the total energy density of their cosmos.
That they could probably get, but only of their local region that they can see, right?
Well, only in the local region.
Yeah, they can.
But not just their universe. The mother of all origins.
No, they could.
Bang of every little multiverse.
No, they could not. They could not look beyond that. They could only.
So that means you could never get a complete theory of the universe.
Or better said, you can never get a. You can never. It's difficult to test this basically because you don't have access to the other regions. Indeed, it is very difficult to test this.
That's a theoretical dodge right there.
Yeah, you can basically, the only thing that this other experimenter in the other universe could do is they see quantum fluctuations driving fluctuation in the CMB, maybe bigger in his universe. He may come to the same conclusion that is the most natural thing to get a big universe from a causally connected region is this inflationary process, and then you can speculate, as we do, that if this happens once, it will do it infinitely often. But he cannot go there and test this directly. There's only one kind of thing I will show you later how you may be able to see that there's at least one, that there are more regions of space-time.
So just before you answered his question,
Yeah.
you said that these different universes could have different, what we call constants of nature.
They could, because that comes when you go, for instance, to a theory like string theory, you will find that different values of these scalar fields that may drive inflation, they also define the cosmological, the different constants of nature. In a theory like string theory, you have no independent constant of nature. They are all expectation values of some dynamical fields. And since they evolve during inflation, the constants can evolve, at least when you jump from between these large regions of space-time. The fine structure is, for instance, one. The fine structure constants is set by the expectation value of a scalar field. If that scalar field moves around during inflation, different regions of space-time coming out of inflation will have different fine structure constants.
But we would never see those.
We don't see them directly. No, we don't never see them.
We can't see them.
We can't see them. They are out of causal contact. I mean, you would have to move basically superluminal to go there. And since you can't, at least I still believe we can't, despite the opera results. Then you cannot go there, basically. I mean, you could go there. I mean, it depends on where you come from. If you come from a region which does not do inflation anymore, you can leave that region eventually, but you can never come back. Right? I mean, you can never talk back. That's the problem once you go into this other regime. But of course, you could probably do the following. An observer that can live infinitely long and never dies and has infinite information capacity, or almost infinite, and just goes on a long space travel and always maps a CMB, will eventually see the CMB changing its properties. He will see it, but he can never communicate it back. It's a kind of very lonely enterprise, if you want to do that. He can never transmit it. It's only for him or herself. this kind of observation that he may do. So, but anyway, this is basically the situation. If you had a situation that you have scalar fields and they have a potential that's more complicated than just one bubble, you can even have regions where in the eternally inflating multiverse, where the different scalar field, basins of attraction are realized, like local minima. And they can, if the theory behind that is this way, they can even determine different kind of low energy physics via the constants of nature, which may be expectation values of fields. So and then the question is, of course, how do I get between these different local minima, right? There are like barriers between. How do I get from here to there? Even this is possible because you can tunnel. The process from quantum mechanics that a particle can go through a classically forbidden wall. If you just wait long enough and make enough tries, there's a small probability that the wave function penetrates the wall. The same thing happens for quantum fields that have scalar potentials, where the scalar potentials makes a barrier between two different regions of the field, where the field could sit here, have that value, or have that value. These are minima. Classically, it could not, when it sits here, go there, but it can tunnel. So all these regions become even accessible. And you will have, basically, therefore, then regions of space-time where inflation proceeds in all possible ways that you get from such a landscape. This is a kind of really weird statement that if you have such a theory, it will realize every possibility that is there in the theory. Everything that is not completely forbidden by some conservation law will be realized, and it will be realized infinitely often.
Good question.
Yeah.
So you're saying that fundamentally underlying all these different multiverses there is quantum mechanics. Is it the same all the way through all the multiverse?
The quantum mechanics is the same everywhere. All this stuff is assumed to be governed by basically by a relativistic version of the Schrödinger equation, right?
Okay.
The wave. If you really write down the wave function as you probably maybe have seen it, you write it as a functional equation on operators. This is how you treat the quantum fields. This functional differential equation is the Schrödinger equation.
Okay.
This is not changed. Everything still. This all proceeds under the assumption that quantum mechanics is fundamentally true.
All through all the multiverses.
Through all the through. Even string theory I will shortly to talk about still assumes that quantum mechanics is not changed. It changes the way how it treats gravity in the context of quantum mechanics. It must do, because general relativity gives you problems together with quantum mechanics. It would have you basically everything crunching. Quantum corrections would eventually crunch into black holes because it would just everything would get strong. But string theory does not change quantum mechanics. I do not actually know whether anybody has ever tried to write down a quantum theory of gravity by changing quantum mechanics, because nobody really knows how to change quantum mechanics without completely screwing it up. Yeah. Right? So this is some kind of pictorial representations of these different, regions where inflation ends, surrounded by still inflating space-time. You get these each region is like a bubble, if you want. They're sub-bubbles. Each of them may be filled by some more or less normal universe. There could be weird universes which are very hot or which are very asymmetric. But outside these bubbles, inflation still goes on because it never ends everywhere. So, and now the question is, of course, if I want to have this scalar field driving inflation and having many different local minima and then going around to basically, I could make this up, but the question is, do I have any reason to believe that such a system could be there? Not just a simple bubble. The simple bubble I can write down by hand. So the one theory where we have some evidence that such a thing is really there, this is, if we want, a really crucial thing where you get your theoretical motivation why to think that there are many different minima for the scalar field and why each of them may describe different physics, is string theory. This is, as you may have heard, it's a candidate for quantum gravity. We don't know whether it's the right theory of quantum gravity, but at least it's one that does not have the obvious normal quantum mechanical problems, like infinite results for quantum theoretical calculations. They are not there in this theory. And why they are not there? Because you replace every known particle, the whole particle picture, by tiny little wiggling loops or strings. They have length. And if something has length, it cannot interact like a point. In particular, it cannot have point-like interaction locations in space-time. And once you have that, you see that if you write down these kind of you see how they propagate. A closed string, like a small loop, basically, it propagates through space-time. It can basically forms like surfaces in space-time, like trousers. And these trousers can have loops in them. And for those of you who have seen the Feynman diagrams of quantum field theory, this is like a Feynman diagram, but you see that because of the length of the loop, of the string itself, you can never draw this together into a point. And this is why all the infinities that you get in quantum field theory treatments of gravity, they are gone. They're just gone. This is one of the nice things about string theory, why people got excited in the first place. Now the point is you can now try to analyze what happens when you really write down a theory of these moving strings and you quantize it in a consistent way. Then you find that for the strings to have, I mean, they vibrate, you write down the quantum theory of the vibrations. For this to be a good spectrum of vibrations that doesn't have any kind of mathematical pathologies or inconsistencies. So if you want for these strings to play a good music, they need to propagate in 10 dimensions of space and time. And they need, by the way, also something that is called supersymmetry, but I will not go into this here. So you have 9 space dimensions, 1 time dimensions. If you don't do that, the strings will basically sound very, very badly. They don't, basically, they have the wrong spectrum of vibrations. Now, if I have 10 space-time dimensions, and I've only seen 3 space-time dimensions and 1 time dimension, what do I do with the other 6 space dimensions? We haven't seen them. We have never noticed anything like that. So the one way that basically you have to exploit then is you have to kind of wind them up. You have to make them very small. You fold them into themselves. You make them into tiny balls or tiny circles if you want, right? And the thing is, if you try to do this in a way that is consistent with physics that we may expect to see at the LHC, like if you want, for instance, supersymmetry there, like a supersymmetric extension of the standard model of particle physics, then there are ways to wind up the internal, these extra 6 space dimensions in a way that they do produce something that looks a little bit remotely like, you know, particle physics at the LHC, not exactly yet. And then these internal 6 dimensions can look like this. They are completely weirdly scrunched up into some, you know, compact space. And then the diameter of this space has to be so small that you could never have, you know, gotten any particle moving in that direction. So the idea is that if you have a single extra direction and it is a circle, then you know if you describe the particle in quantum mechanics as a wave, and you put a wave on a circle, it has to be a standing wave. It has to go back into itself without canceling out. That standing wave gives a maximum wavelength the particle can have in that direction. And maximum wavelength means a minimum mass, minimum energy. Now, the smaller the circle, the larger this mass scale. So you make these things so small that you could never have excited it, let's say, in a particle collider, like the Large Hadron Collider. And that means the diameter must be less than 1,000th of the proton size, roughly, very roughly. And typically, they tend to be even much smaller. But this is how you get rid of these 6 extra dimensions in the first place, because you haven't seen them. Now, the point is, if you do it this way, if you get rid of them this way, you pay some people would say a price, maybe too heavy a price. I mean, this is a picture how space-time could look like in string theory, right? Our large space-time dimensions, and at each point, it's associated, sits a tiny knot of curved up extra dimensions, 6 of them. These are, I mean, I took the example here, these Calabi-Yau shapes, the basic Calabi-Yau spaces that give you, you know, particle physics which are not too bad. The point is now you have to ask, if I get rid of these 6 extra dimensions in string theory, how many ways do I have to do that? I could just choose, you know, a tiny 6 sphere, fine. I mean, a 6-dimensional analogy of a ball. But there are different ways. And then you can you have to ask how many there are, which give inequivalent physics in the end. And the point is that there are exponentially many. There are so many that we don't even know how many there are. This is, if you want, the price that you pay in string theory. You have a more or less unique theory that is consistent on the quantum level, but it has so many solutions once you want to describe something 4-dimensional that we do not even know how to count them all. And even worse, I mean, even beyond that is the point, even if I stay on just one of these ways to curl up the extra dimensions, then if they should give something like our particle physics, and maybe together with supersymmetry, because people like this for its quantum mechanical properties, then you find that even a single of such spaces, it can be plucked and pulled in different ways. It can be deformed. It's like you can blow it bigger and smaller. You can stretch it. You can twist it. And there are some of these deformations which leave the basic properties of these compact extra dimensions then unchanged. And all these allowed deformations, they behave like massless scalar fields in 4 dimensions, like many massless scalar fields, hundreds of them, maybe 1,000. Now, 100 massless scalar fields are bad. They all mediate couplings of the strength of gravity, and you would have, 5th, 6th, 7th, and 100th forces flying around, of which none have seen. So you have to, in addition to basically count all the different ways you curl up the extra dimensions, you have to basically find ways how to make these allowed deformations, which are scalar fields, massive. How to give them mass so that they cannot mediate long-range forces anymore. This is what the people call modular stabilization. And this is only like in the last 10 years have people started to learn how to do this. So, but the point is then, is like if you give them masses, okay, now these scalar fields are massive, fine. They don't run around anymore, they don't make long-range forces. But if I have 100 scalar fields, and each of them basically is kind of corresponding to these, they measure the size of these holes, these deformations in this kind of scrounge. As I said, they measure the deformations and therefore also the size of these holes. Now, you look at how many of, when you make them massive, how many of minima do you get? Their scalar potential, this is what you want to calculate now, once you make them massive, right? How many minima do they have? And you get that if you have 100 fields, scalar fields, 100 allowed deformations, you have stabilized them, you make them massive so that they are not massless fifth forces anymore, you get of the order of 10 to the 100 different minima, even on one type of rolling up the extra dimensions. So even on each single compact extra dimension choice, you get a landscape of 10 to the 100, maybe 10 to the 1,000 different vacua with all different, all locally, quadratic bowels separated by walls in the potential, in the scalar potential, and all of them having different vacuum energies. So this is what people call the string landscape. You have an unknown number of ways how to curl up the extra dimensions, and each of them, if you manage to stabilize it, has already like an extremely exponentially large number of different ways of stabilizing it, giving mass to the scalar fields, getting the scalar potential there. So you have, and as I said, these scalar fields, they determine not only the sizes of the extra dimensions, they also determine the low energy physics. Each of them sets in some combination some gauge coupling, for instance, some new Carver coupling. All our so-called constants are set by this. So that means if you have now these 10 to the 1,000 different vacua where all these scalar fields have slightly different values, the constants change. And now you put eternal inflation on this, which moves you around, lets you jump around in the scalar fields. You get that all the different regions you generate in the universe have different effective four-dimensional physics constants. Yeah? This is this whole so-called landscape picture. So this is some kind of pictorial. You have this, as I said, the scalar potential as a function of here two scalar fields. As I said, with this local minima, we have seen that I had before. And at each local minimum, the value of the scalar fields make the extra dimensions look a bit different. They are a bit differently deformed. And they also, since they play the role of our four-dimensional low energy physics constants, these constants are a little bit different. Yeah? So this is basically what you are left with if you basically follow this line of reasoning. You have to basically study the ways how you curl up the extra dimensions. Then you have to calculate by getting rid of their deformations as massless scalar fields to give mass to them. Then you get this landscape of a potential for them. And then now what you have to do is find regions that drive inflation, try to characterize their properties, and you have to count. You have to count and see whether you can make any statistics on this humongous set of vacua. Because you cannot hope to make any kind of specific, like we sit here or there. There is no way to hope. You can only hope to make statistical predictions and then look whether we are typical or untypical with respect to the statistics. This is what you basically then can do. And of course, you can basically check. The best hope you may have in this context is that maybe there are some models of inflation that you could write down with normal scalar field theory that are just not there in string theory, or so extremely unlikely that you may have some discriminatory power. And that is something that is basically, that we don't know whether that will work out. There is some evidence that this could work. This could maybe in the future be an accessible point. So what are the consequences of that picture? One is that you probably have heard of this, this so-called cosmological constant problem, right? I told you that we have measured that the expansion of the universe is speeding up. There's a tiny positive cosmological constant, most likely, that does that. But its value is hideously off from what you expect from quantum theory. Yeah? So the point is, this this parameter that Einstein already introduced that gives you this accelerating expansion of the universe, it gets corrections from the loops of virtual particles, from the quantum fluctuations of all the fields. And if you work out what the natural scale, the contribution from this quantum theory contributions is, it's the Planck scale. It's the scale where gravity becomes a strong quantum effect. And this is 16 orders of magnitudes higher than the energy scale that LHC can reach. Yeah? The thing is, if the cosmological constant had that value, you wouldn't be sitting here. Because even a light signal emanating from a point that is 1 Planck length away from me could not reach me. The space would be so hideously expanding fast, it would be ripped apart by the quantum fluctuation at that stage. Now the point is, the real number that we measure is this. It's 120 orders of magnitude smaller than the naive prediction. So there are two options. Either you despair and go home, because this is the worst discrepancy that I've ever seen in theoretical physics. Or, I mean, the only other option so far we seem to have is you take these, on average, if you take string theory with its extra dimensions, and on each type of extra dimension, you have 10 to the 1,000 different, vacua, different minima for their scalar fields describing the shapes of these extra dimensions. If you take them honestly, each of them have different vacuum energy and therefore different cosmological constant. Now you have a huge set of vacua that have all different values of a cosmological constant. And if you have enough of them, you will find among them a few where, just for accidental reasons, they have such a small one, right? Because if I have 10 to the 1,000 and I want something like of the order, something that has value 10 to the minus 100, and I have 10 to the 1,000 and they just scatter flatly with their values around between 1 and 0, let's say, you will find a 10 to the minus 100 fraction of the 10 to the 1,000 that have values of 10 to the minus 100. So now the point is, this is still, we have just done an argument that there are such solutions that will have such a small quantity accidentally. But the final thing basically that goes back to Weinberg actually is that you realize that if you look at what the cosmological constant does to a universe like ours, if it's 10 times or maybe 30 times bigger than what we measure today, there would be no structure formation. The tiny fluctuations in the CMB would never collapse to form galaxies, because then the acceleration is too fast already and starts too early. So there is an argument, a post-diction argument, that says condition given on what we see, we would never expect ourselves to find in a universe that has a cosmological constant exponentially bigger than what we see. Maybe a factor of 10 bigger, but not much. And then if you have a theory that gives you at least a small fraction of solutions where you have such a small thing, then this is enough, because you don't expect to find yourself in the many, many more other ones which are bigger. This is what you call a weak anthropic argument. So the only way how we can resolve this tension is assuming these many, many vacua to be therefore real, to be all realized, populated, generated as regions in space-time by eternal inflation, and then condition basically the prediction on that we have already observed something. It's maybe not very satisfactory, but it's the only way we know so far how to get this ridiculously small number compared to the naive prediction. So that is, if you want, some people call this is a post-diction success of this whole picture. But you could also call this a success because we don't have any better idea. Anyway, if it is true, you agree probably on one thing. This is like the ultimate Copernican picture, right? I mean, you have replaced one universe by an infinity of universes, and everything outside our universe is infinitely bigger than anything inside here. Yeah, I mean, it's crucial, as I said, to make this argument. You just don't need only the statement that if the cosmological constant is 10 times bigger, we have no structure in our universe. You need to have these many vacua that just statistically give you a small fraction where it is that small, right? And that the only theory that does this, seems to generate so many vacua, is string theory. Is the string landscape. So that's basically, I mean, as long as you stay on this track, then, yeah. So here is the one thing where, as in my knowledge, where you could hope to get any kind of handle on testing whether there is really more than one universe. The point is that you have this eternal inflation going on that generates different regions where inflation ends. Each of them is like a huge bubble, like our universe. But these basically, some of these bubbles basically, they still expand the edges of these basically regions. And sometimes these edges can collide. if they are close enough to each other for accidental reasons. If they collide, this is like two soap bubbles colliding. Where they collide, they form like a circle. The circle changes the background temperature density there, and that you would see in the CMB fluctuations. You would really see, this is the spatial map, right? I mean, you will really see, in extreme case, you would see like a circle of temperature deviations turning up. People are looking for this. No, nothing has been found. If you would see that, and you could rule out any kind of statistical fluke, no other kind of then I think this would be the only way you can unambiguously, I mean, then you could actually see there was another bubble, another region of space-time, roughly as big maybe as ours, that has collided with our own. And then you would, this is the only way you can, I think, get evidence. I mean, then you could say if there are two, then there are probably many. Right? That's the only hope we have. But the hope is very slim because you can, if you try to estimate how likely it is that this collision happens at a time when it is still there, and for instance, not wiped out by the inflationary expansion of our part of space-time, it's not too likely that this happens in the right time window, that we can still see it in the CMB. So, and this is basically now, this is the final short part where I will basically show you, as I told you, I mean, how to build, if you want to build inflation, I mean, you have to look at the string landscape picture, how you get inflationary regions of the scalar potential, shallow parts, which drive vacuum energy, and then exponential expansion. And then that there is what seems to be some particular structure in string theory that tells you that you may not be able to get all of the models of inflation that you are normally used to. In particular, you don't get the quadratic bowel shape or something steeper. And that you maybe this becomes testable if you can estimate how often this happens in this whole landscape picture. Yeah, so the idea is, I mean, the basic structure behind that is that there is some notion that people have realized that the scalar fields that come out of string theory, that's deformations of the extra dimensions, right? These scalar fields, they cannot go arbitrarily far. They cannot reach very large values. They are kind of like bounded by the fact that the space itself, the extra dimensions, have been scrunched up. They have been compactified into some small shape, some small space. So, okay, that's fine. I mean, you can build inflation models that do not need a field to go far. But I told you that the ones that basically would tell us at which scale they are sitting, energy scale, the ones that have a very high inflationary energy scale and then make gravity waves that you can see in the cosmic microwave background. Those are the ones that have these like power law potentials, and they want to go far in field space during inflation. You cannot make them while keeping the field moving only a small distance. So the question is then, can you make these things at all in string theory? If I'm telling you that the scalar fields coming from the string landscape, they can only go less than this distance, the Planck distance. So there was at one point a notion that maybe you can't make them at all, and that would have been a prediction, right? That would have been a clear-cut prediction. Then if they could not make them at all, and you measure the gravity waves, the theory is dead, if you had such a statement. Now, unfortunately, we don't have such a statement anymore. You can make these models, but when you make them, they don't look really like a parabola anymore. The power has changed. And what you have to do is, I mean, first you have to convince the theory to make a large field displacement, although the field itself can only go a small distance. So how do you do that? You probably have also at one point looked at the logarithm of a complex number. A logarithm of a complex number has a funny property. The complex number you can make go, it's like it has two components, like a vector. You can make go around the origin, right? Going on a circle. So like the angular part of the complex number has a finite range. It's 2 pi, right? I mean, it makes one circle. But the logarithm of this grows even when you move beyond 2 pi. It grows without bounding. It makes like a spiral, a staircase shape. So the path that this function moves while you go many circle after circle after circle in the variable phi, this path is infinitely long, although the variable itself has only a finite range. The mathematicians call this monodromy, a failure to return to yourself if you walk once around. This is this Greek word monodromos. I walk once around. I'm usually expected to come back if I walk once around. This function does not come back. It goes on forever. There are effects in string theory that do this, that basically generate a potential energy for a scalar field, where the scalar field itself otherwise is it's limited. It's like an angle. But the potential energy behaves as if it were not an angle, but could go forever. Yeah? There are ways to do this, which involves basically what we call D-branes. These are basically like, places in space-time where a string can end. And these D-branes, they kind of like, the easiest way to think about this is, if I go back once here, is that these D-branes are places where strings can end, and the strings stretch between them. Now move one of the D-branes. As I told you, if they intersect, move them like this so that their angle changes. Yeah? This was this picture that I had here. So if there's a string stretching between them, then it will get stretched longer. And since it has a tension like a rubber band, it will feel that it gets stretched. So there's energy built up. Of course, the angle between the two branes is periodic. It always comes back to itself. But if the string stretching between them winds up more and more, if you turn them multiple times, you will get more and more and more energy in the string, although the angle always returns to itself. You generate this kind of failure of this monodromy. And then you can build basically now this way a potential energy that behaves as if there were a large field displacement. That has been done. And then what you find is when you calculate, it's a long technical calculation of how the shape of this potential energy looks like, it is not phi squared. It's not a parabola. It could be linear or some fractional power, almost like a square root. That's really weird. We have not found any place how you get this parabola for that. The parabola is a naive expectation, but it always kind of gets, like someone steps on it. And if that were general, you could then try to, of course, discriminate this against simple parabola shapes for an inflationary scalar potential. And there are ways to separate them in the data. Because when you look at the CMB fluctuations, you can extract, when it comes to for inflation, two properties. You can see basically to the power spectrum of the density fluctuations coming from inflation. And one property is beyond the sound waves. These are all like local physics in the plasma that decouple when it decouples and sets the photons free. But beyond that, you can look at whether the overall distribution of this power spectrum is a function of wavelength, and this is then, in the spherical harmonics, wavelength goes into the multiple moments L, whether this is flat or not. You can look whether it has a tilt, whether it's not exactly equal power on all different L's. They don't, but these are the sound waves. You basically can, this is local physics, just from the magnetohydrodynamics there, if you want, coupled to gravity. You can subtract it out, and then you can look whether the remaining original shape is just a flat line that's exactly horizontal or not exactly horizontal. That's the tilt. You can measure this. You can constrain it from this kind of shape. And then you can look in the polarization of the cosmic microwave background whether you see these gravity waves. And then you can constrain them both. This is what the WMAP satellite has done, and which PLANCK will do much better. So you see already some evidence that the spectrum is not exactly flat. There is some slight tilt, very tiny. But it's not exactly red. And this is, from inflation, you expect this, because the field rolls down. Therefore, these quantum fluctuations cannot be going on forever. And therefore, they must end eventually, and therefore, it must become smaller. So we expect this kind of slight red tilt. But you see, they haven't seen any gravity waves. They only give upper limits. The quantity R that I was telling measures their strength is bounded from above, basically. So, but the point is, you can now look at how these different potential shapes, they basically always give you these two numbers. For each different shape of a scalar potential, you get two numbers out here. This is the one for the quadratic shape that gave you this, would give you measurable gravity. You see, if that were true, you might already have seen it in these measurements. You would not get this, but some kind of blob here of detection in these error contours. And the ones where you don't get quadratic but lower shape, these ones here, that always seem to come out of these string constructions, they are sitting still here, but they are lower. And if you would have a measurement of that precision, which Planck, compared with some ground-based experiments, will do in a few years, you start to discriminate between them. Now the question is, of course, these kind of things. Is this a strict answer that you can never get the power 2 that you get from field theory? And then, of course, how often do you get them? Because there are many of the models where you see no gravity waves, where the field just moves a tiny distance. You have to basically now study questions of how often is this realized? How many of these different constructions there are? And there we only start to, we're at the very beginning to get any understanding of that. It is like the same kind of counting you make for trying to explain the cosmological constant, you have now to make for different types of inflationary models. And that's where we are at the end. Basically, the best hope we can to, these kind of ideas about the landscape, about these many vacua, the many universes, they are kind of consequences of this picture of eternal inflation. They are logically following from that. But testing this would rely on a combination of either being very lucky and seeing such a bubble collision, like the collision between two neighboring regions, between our and another region, and or getting any handle on whether there's any tendency in string theory that tells you there are some inflationary models you can't get, or you get only very, very rarely. And if you happen to measure one of those, you can disfavor the theory. But we are not there yet. Thank you very much.
It's awesome talk, Alexander. I'm trying to imagine what things are like in these other universes. Pointed out that it's most likely that they're going to have different gravitational constants or Einstein's constants. So these things are, there's got to be no formation of galaxies.
In many of them, they will look completely different. Yes, if their cosmological constant is bigger, for instance, they will be just, in a sense, de Sitter space already, right? They will undergo accelerated expansion much faster than here, which means they will have exponential expansion. The cosmological constant does inflation. It's just, we don't call it in our universe this way because it is so small. And until now, other forms of energy have dominated, or until recent in the sense of 5 billion years ago. But
so with no way
the other ones, you would, if there's a bigger cosmological constant, they would be empty and just very quickly expanding.
Right. And no gravitation inside of the universes as well?
No, gravitation is there, but there would be no structure forming, because a fast exponential expansion coming from a bigger cosmological constant just rips all the structure apart before they ever have a chance to collapse. Yeah, this is this argument by Weinberg. You can basically argue if you have a given level of density fluctuations, 10 to the minus 5, let's say. Then you calculate the time until you have your fluctuations. They evolve with time under gravity until they go nonlinear. Nonlinear means they collapse under their own gravitational force. Once they cannot be ripped apart by some cosmological constant anymore. Like in our galaxy, that doesn't expand because of the cosmological constant we have. Only very large distances between galaxies feel this repulsive, this kind of accelerating force. But if the cosmological constants can rip apart the initial density fluctuations before they have the time to go nonlinear and collapse under their own gravity, then they will never collapse. And the universe will be empty and boring. And this will happen very often. This is the majority of all universes on this picture. We just don't happen to live there because then we would not be there. Yep.
So where does the matter and energy come from in our universe?
Oh, that's a good, I actually skipped over that. It's a very good question. This is, now, assuming that our universe came from some inflationary phase in one of these potentials, once the inflationary scalar field starts to roll more quickly towards the minimum of its potential, the minimum of the bubble, then it converts its potential energy into kinetic energy. And that means it begins to oscillate around the minimum. Like a ball. If you take a ball in a bowl, you let it roll, it begins to oscillate. Now, the inflationary scalar field will have couplings to other fields in general, even through gravity already. Gravity couples everything to everything in a quantum theory. But there will typically be more couplings. If you do this in any complete picture, like in string theory, you will have couplings to other fields. And then while it oscillates, it will have a decay rate to these other fields. And these other fields will take over the kinetic energy that the inflaton field has, and this will create a heat bath. So this way, the inflaton, it's like a condensate, if you want, like a Bose condensate, will, on the long run, decay into all the other particles it has couplings to, and will produce them with large numbers and large entropy, and will heat up the universe. This is what is called reheating. This is very model dependent, because you have to really then specify how the inflaton scalar field couples to all the other fields of the standard model, right? But this is basically how this happens, just by decay processes. This is like, I don't know, how shall I, let me see. If you have an example from normal quantum field theory, from our standard model, if I give you like two very energetic photons that are energetic enough like in a background electric field, they can spontaneously like convert into an electron-positron pair. So they decay because they are energetic enough and they have the right momentum configuration. Now a scalar field that has lots of kinetic energy, and by the way, it has a mass scale which even for the inflaton is very high compared to the masses of our elementary particles. It can just decay into them if the coupling is there. And that's the model-dependent part. I mean, you have to specify then how the standard model fits together with, how that interacts with the inflationary scalar field. And that would be, that's a question that, you can ask this in string theory, because eventually string theory describes also particle physics. You have constructions for that. You can then ask for a given construction if there's also an inflationary scalar field, how they couple. But this, again, you will have myriads of answers, right? Because you have this gazillion of different solutions.
Hello, behind you. Hi.
Hi.
A very quick yes-no question and then a more sort of detailed question. The yes-no question, are you assuming the Planck length is the same across all the multiverses?
No, it will vary. Okay. The Planck length is not fixed, because this is also an emergent quantity. It is a VAV of some scalar field. Okay. Right? Like the volume of the internal 6 dimensions, the 6 extra dimensions, they have a size. This size determines the 4-dimensional gravitational constant, which determines the Planck length.
Gotcha. And the sort of more complicated question is it possible, like if two universes collide and you have a bubble remnant, that implies that there is an edge to universe A and universe B, and
it's not an edge. It's more like there's more like a domain wall, some wall separating them, like a crossover region.
Okay. Yeah.
Space doesn't end there, right? It's
right.
Just that the properties of different fields and in the different regions, they will cross over between the one and the other.
So they're adjacent in some.
They're adjacent, exactly. And
so could you get a mechanism? So my question is, could you get a mechanism similar to Hawking radiation, where you have two vertical particles, one goes beyond an event horizon and the other stays with us? What if virtual particles form as a pair right at this border? Is it possible then that one would go into one universe, the other would go into the other universe, and in some way we can therefore get information about another universe?
Well, of course, in general, you could have a pair. If you have a pair of particles forming there, one of them might go over. The point is that this boundary between the two bubble universes, in general, by itself, just by being a boundary, is not a horizon.
Okay.
What happens in our situation is, because we have our tiny positive cosmological constant, and it already now makes up 2/3 of our total energy budget, although it is so tiny, just because it doesn't get weaker.
Does the Obama administration know about that?
They probably know, but so far you can't make money out of this, unfortunately. You can't convert lambda into dollars. But the point is that because it is already accelerating our expansion, and all the other energy forms in our universe, matter and radiation, they dilute, of course, the bigger it gets, right? They dilute. The cosmological constant does not. A potential energy of a scalar field, if you want, or a vacuum energy, which all are making up cosmological constant energies, they don't dilute. They have a constant energy density. It's basically, they borrow from gravity, and this way basically stay constant in energy density. They make a constant, like, this is the only free lunch that I've ever known of. There is really a free lunch. You can borrow unlimitedly, it looks like, against gravity. This is like really, you can go forever on with deficit spending this way, but only there. Anyway, the point is this exponential expansion that is setting on, even for us now again, that creates a horizon, a maximum distance where we can look. And we cannot send light beyond that, and light that comes from there would not reach us. So this is like living, turning a black hole inside out, and then making the inside the outside and living there. You know that inside a black hole, I cannot send a light, it comes back, so to speak. Now you turn it inside out, then you're living outside, and you are basically seeing some sphere around you, and you can't get out. You can't come from the outside to the inside of the sphere. That's a horizon. So there you have something like this. And indeed, there you have an effect, like Hawking radiation. The particles, you have quantum production of particles, and one of them goes to the outside, is lost, and the other one comes in. And that is the origin, if you want, in the end. There is with every de Sitter space, with a positive cosmological constant, there is a tiny amount of radiation involved, like a temperature, a de Sitter temperature. It's like the Hawking temperature. It's the exact analogon. And the point is basically if the de Sitter space is large, which is the case if the cosmological constant is tiny, then this temperature is tiny and you will never see it. But if the cosmological constant were big, like let's say a thousandth of the Planck scale, then you would have a temperature which is a thousandth of the Planck temperature. That means that universe is hot just because of this Hawking radiation already. And you don't want to live there, at least not if you are carbon-based.
From that graph, can we now say that the...
Did I kill it? Sorry. Which graph?
Yeah, can we now say that the parabolic model of inflation is dead because of these observations?
No, not yet. You see, this is 1 sigma.
Okay.
This is 2, whatever. This is 2 sigma. So there were other shapes. This is not a parabolic, but a quartic bowl. That is dead.
Okay.
Unless you, I mean, the simple quartic bowl is really dead. I mean, it's like 3 sigma, more than 3 sigma now. The other one, Planck will probably be able to say whether this is there or not, the quadratic bowl. Because Planck will basically limit the error on this axis to something like 0.05 maybe. And then the error in the tilt of the density fluctuation spectrum will be something like less than one of these marks here. It will be so it will basically create a very narrow strip, so to speak, of this length like 0.05 and the width of less than 0.01 here. So if this strip would sit here, right, what it sees, or if it sees another, is it like here, then they would rule it out. Sorry, yes.
How this multiverse concept is related to Lee Smolin's idea of this grand evolution between universes?
This is a good question. I confess that I am not too familiar with loop quantum gravity. This is what you're asking about. This is it's a competing theory of quantum gravity, where we basically, as well as the string theory, we don't know yet whether it corresponds to anything real. I mean, in the real world. It has its own problems. As string theory has its own problems, like with having too many solutions. With his, I think his idea, you talk about his ideas of actually that somehow like the proliferation of black holes, right, would kind of like can give rise to new universes. And if you have more black holes, you generate more universes. Therefore, eventually you can maximize whatever the appearance of structured states in the universe, and in the end, maybe even life or something like that. From what I know is that this has to assume that a black hole actually is something like a funnel to a new universe, right? Something like a white hole on the other side or something like that. I'm not sure. I mean, you have to make assumptions for that. These assumptions rely on typically on something that is called quantum cosmology, where you try to define a wave function on the space of universes and then estimate the probabilities of whole universes to be nucleated from nothing, or let's say through a black hole transition. I admit that I don't know enough about that to judge whether this makes sense or not. I know that the way how quantum cosmology is done is basically you have to kind of like rotate time with an eye so that it becomes like space. But then you're not doing the real normal dynamical field theory anymore. So there are questions there. And in particular, the black hole transitions that Smolin is talking about, they do not have to do anything with the transitions between a landscape of different potential energies for scalar fields that come via tunneling or quantum jumps of a scalar field. I think they are different avenues of trying to connect different universes. The one does not necessarily have anything to do with the other. I do not see how I can get predictions from this thing about his idea, because in particular, this thing doesn't assume anything about bridges between one side of a black hole and the other side.
Okay, well, Alexander, we have a little black hole collector there in an Are We Alone cup.
Wow, thank you.
And please join me in thanking Alexander for his great talk.
Thank you.